Hello, welcome. This is Organic Chemistry 2341, Homework Chapter 2. So let me go ahead and share my screen and we can begin. All right, so what we're going to do is we're going to go through that Chapter 2 homework. So the first thing we want to look at is classify each of these compounds as to whether it's an alkane, alkene, alkyne, alcohol, aldehyde, amine, and so forth. So what we're looking for is those functional groups that we're going to see. And the first thing we notice here is this has a carbonyl on it. And so we look at the several different functional groups that we have carbonyls, and we see that it has bonding to two different carbons. So we know this is a ketone. So this is ketone right here. So this is a pretty obvious functional group. We have a cycloalkane plus an OH group, which turns it into an alcohol. Alcohol. And this is also an alcohol, but it's just not in a ring. This right here, because we have the triple bond, is an alkyne. Alkyne. Okay, we have that carbonyl again. And so that could be a ketone, an aldehyde, a carboxylic acid, or an amide. But we have one carbon bond and one hydrogen bond. So that means it's an aldehyde. Aldehyde. Okay. And then this last one right here, we have hydrocarbons right here, but a double bond. So that turns it into an alkene. So we have alkanes here. We have ketone, alcohol, alcohol, alkyne, aldehyde, and alkene. Okay. So let's move on to the next question here. We want to look at all the different functional groups available to us. So we're not going to identify things that are alkanes, but anything other than an alkane we want to identify here. So what we're going to see here is that we have each of these counts as an alkene. So that's one functional thing we have. And this is an alcohol. So in this molecule here, we have an alkene and an alcohol. If we look on to number B here, we have this structure here at the end. It's carbonyl with an OH on it, so it's a carboxylic acid. Okay, a nitrogen bonded to a carbon, so that means it's an amine. Okay, amine. Okay, now we have a carbonyl bonded to a nitrogen, so that makes it an amide. So we just changed that one letter, but see the difference is one is bonded to a carbon and one's bonded to a carbonyl. And then we have this right here. Okay, instead of having the OH, we have an O in some other alkyl group, which turns it into an ester. Okay, so carboxylic acid, amine, amide, and ester. So if we look at this one right here, what we see here is this is the phenyl ring or benzene. And I'm going to just list that because it's something we see from time to time. And then this nitrogen's only bonded to a carbon, not a carbonyl, so that turns it into an amine. Okay, so let's look at this one over here, cholesterol. Yay. Cholesterol is very close to vitamin D3 here. Again, we have an alkene and we have an alcohol. So those are the two functional groups we find in those cholesterol. Okay, in demerol here, we have a nitrogen bonded to three different carbons. So that gives us a tertiary amine. And we have this functional group here. It's a carbonyl bonded to an O bonded to a carbon, so that's an ester. And then I'm going to circle the phenyl ring again right here. So let's look at this one. We have an alkene right here, and we have at the end here a carbonyl bonded to a carbon and a hydrogen. So that's an aldehyde. Okay, and this one right here, we have this is an ester, this is an ester, and this is an alkene. So just by visually looking at those things, you're going to look for those structures that signify those different functional groups. All right, next thing. There are 7 isomers of the compound C4H10O. Write their structures and classify each by functional group. Okay, first of all, whenever we see a structure like this, we're going to start out with the simplest one, which is the longest one. So we're going to go 1, 2, 3, 4 carbons plus an OH. Now we have CH10. Let's double check, make sure we have the right number of hydrogens here. One, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have the right number of hydrogens. So we're going to draw this again, but we're going to do it in skeletal form. 1 carbon, 2 carbon, 3 carbon, 4 carbon, and then an OH. Okay, so that's our first structure. We always want to start with that linear structure because it's easier to build up from there. So what we're going to do first is we're going to move the OH from the end of the chain to the middle of the chain. Just doing it that way, right there. So that's going to be a really good way to, look at all of our different isomers here. Now, we can't just move it over one more because it'll look the same, and we can't move it to the other end because it'll be the same compound, right? So now we have to do something else. So we're going to take our chain here, and what we're going to do is we're going to actually take a methyl group off the end, and we're going to move that over here. And that's going to give us our third isomer. And then we're going to move that again, OH right here, from that 2 position over to the position right next to the alcohol. And that's another isomer. Oh no, that's the exact same isomer as this. So we can't do that. So that's the only isomer we can get by just moving the methyl group. So let's try for another one. Okay, so let's look at another one. Let's see, if we moved a different structure, then we could do it. Let's see, 1, 2, 3, 4, OH. Okay, so there's another one. So let's think about this from a little structure side. If we put a little squiggle here, that would be the butyl group. If we put our squiggle here, that'd be the sec-butyl group. If we put a squiggle here, that would be our isobutyl group. If we put our squiggle here, that would be our tert-butyl group. So whenever we're thinking about isomers with 4 carbons, we can start with those 4 structures that are those substituent structures we have that we can use. Okay, so that's only 4. So we have to change something else. There are no possible other things we can do with the alcohol, but we have another functional group we haven't even tried yet. So let's do 1, 2, oxygen, 1, 2. So see, this is going to give us that same empirical group. And let's see, so that's symmetrical. So let's put a methyl group on one side and a propyl group on the other. And wait a minute, propyl has 2 isomers. It has N-propyl, but it also has isopropyl. So I bet the last one is going to be our isopropyl group here. So by thinking about the different little substructures we have and adding them group, we can get all the different little isomers right here. Notice we ran out of isomers for butyl here. So we went to this ether as our next structure, and then we went through the 2 different isomers for propyl. All right, moving on to the next question here. Classify the following alcohols as primary, secondary, and tertiary. Remember, we look at the carbon the OH is bonded to. The classification of that carbon tells us which kind of alcohol we have. So this carbon right here is bonded to one other carbon, so that makes it a primary. This carbon right here is bonded to 2 carbons, so that's a secondary. This is bonded to 3 carbons, making it a tertiary. This one's getting a little harder, but it's also bonded to 3 carbons, so it's still tertiary. And this is bonded to 2 carbons, so it's a secondary. So look at the carbon that the OH is bonded to and look for look for how many other carbons are bonded to it. Remember, that same qualification goes for alkyl halides. It'll go for hydrogens that are on those carbons. They're primary carbon hydrogens if they're on a primary carbon. All right, next question. Classify the following amines as primary, secondary, and tertiary. Amines and amides, the nitrogens are the only ones that are different from that classification. The alkyl halides, the alcohols, the hydrogens and carbons are all classified by how many carbon bonds to that carbon they have. Amines are different. It's how many carbon bonds to the nitrogen you have. So what you look for is how many carbons are bonded to the nitrogen, and then you classify it. So we have 1, 2, so that makes it a secondary. We have 1, 2, 3, that makes it a tertiary. We have 1, 2, that makes it a secondary. We have 1, that makes it a primary. We have 1, 2, which makes it a secondary, and we have 1, 2, 3, which makes it a tertiary. Now, the other way to look at this is you can say how many hydrogens are attached, okay? If there are 2 hydrogens on the nitrogen, it's going to be a primary. If there's 1 hydrogen on the nitrogen, it's going to be secondary. If there are no hydrogens on that nitrogen, it's tertiary. So use one of those 2 methods to identify these amines. All right, moving on to our next one. Write the structural formula for each of the following. And we have a whole bunch of different things to do. So 3 ethers with the formula C4H10. Okay, so that's a different formula than we had before, right? So let's see, ether. So we're going to start with this, and we're going to do symmetrical. So that's 4 carbons, and that's 1, 2, 3, 4, 5 hydrogens, 6, 7, 8, 9, 10 hydrogens. So we have the right number of hydrogens, the right number of carbons, and we have an ether. Remember, the ether is the carbon-oxygen-carbon functionality. So then let's see, I guess we've already done this on the last one where we did this one right here as an isomer, and we have the other propyl isomer, isopropyl. Okay, so let's go ahead and double check. Okay, they each have 4 carbons, they each have 1 oxygen, and they each have 10 hydrogens. So we've completed number A. Okay, so let's see, let's move on to C right here. A secondary alcohol with the formula C3H6O. So let's do C3 right here, and then we're going to do hydrogen, 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 and it's a secondary alcohol, so we have to put the OH there and a hydrogen here. Is that right? Let me see. 1, 2, 3 carbons, 1 oxygen, 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. So we have completed, so actually it looks like we have 6 hydrogens here. So we have to get rid of 2 hydrogens. Ooh, how do we do that? Well, the easiest way to get rid of 2 hydrogens is to put a double bond between 2 of the carbons right here. So let's see, that's C3H6O. 1, 2, 3, 4, 5, 6 hydrogens, 3 carbons, and 1 oxygen. So that's how we get to that structure. And so what I'm going to do is I'm going to redraw it without the hydrogens to show you what the skeletal structure would be. And so what that's going to look like is we have to have a secondary alcohol, OH, 3 carbons, and then our double bond. Okay, so that's C. Let's go ahead and do F right here. Actually, let me do F on the next page. All right, so we're going to do F here. 4 primary alkyl halides with the formula C5H11. So let's look at C5. Okay, 1, 2, 3, 4, 5 carbons. And if we have a bromine here, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 hydrogens. So we have the right structure to start with. Now we can start looking at different isomers. Okay, wait a minute. Didn't we talk about different possibilities for isomers of butyls? So let's use that same kind of concept to see if we can do it. We're going to take this methyl group off the end and we're going to move it over. We're going to keep this bromine here. And so we're going to put a methyl group there. So this is 1 isomer, 2 isomers. So all we've done is moved this over to here to give us another isomer. We're going to move that over one more time. to give us, oh, here, there's a, right here, that gives us a different isomer. So that's, let's see, 4 primary alkyl halides. So we have, those are isomers there. If we move the methyl group over one more here, that's going to make this a secondary alkyl halide. So we can't do that. So what we have to do is we actually have to then take the methyl at the end here and move it one over. And when we do that, we end up with this alkyl halide. So those are the 4 alkyl halides that we can create with this structure that are primary. All the other isomers would have to be a secondary or a tertiary alkyl halide. So let me erase some of these notes here so you can look at the different structures we have. So all of them have a primary alkyl halide and have that 5 carbons in them. 1, 2, 3, 4, 5. Yeah, just double check. Okay, so let's look at letter, let's see, I, and no, so now we're up to I. 3 aldehydes with the formula C5H10O. So I'm going to redraw the last isomer over here, and we're going to draw those 3 isomers of an aldehyde. So when you're given something like that, let's start with actually drawing the functional group first, because our aldehyde is going to be H right here, bonded to a carbon. And this is one of the carbons, so we only need a 4-carbon chain on there. 1, 2, 3, 4. So that's our first isomer. Okay. So then again, what we're going to do is we're going to take something off the end and move it over 1. So our next isomer is going to go to there. Okay. Why can't we just move it over here to where the hydrogen is? That would change it from an aldehyde to a ketone. So we can't do that. So, but we can still move this methyl group over one more time and give it another, let's see, 1, 2, 3, and have a methyl group there. So that's going to give us our 3 different things. Our functional group has not changed. We're having that aldehyde each time. The only thing that changed was that end chain. Okay, so let's go off and do the last 2, J and N, right here on the next slide. And let's see, what we have with J is 3 ketones with that same structure. Okay, so when we start with a ketone, we have to start with a methyl group there, and that's 1 carbon, 2 carbons, 3 carbons, 4 carbons, 5 carbons. So this is the simplest ketone we can get. We have our long chain, we put that ketone near the end. Again, we can't move this carbonyl to the end because it would turn into an aldehyde. So we have to, let's just move the carbonyl over 1. And that'll give us another isomer. So if we move the carbonyl at 1, 2, 3, 4, and the carbonyl would be down here. Now, if we moved the carbonyl over 1 more, it would actually look like the original molecule here. So we can't just do that. So now we have to do that trick where we start changing the long chain. And so let's see, let's change this longest chain. So we're going to draw our ketone first, and then we're going to take this in group here and move it over 1 carbon to give us our 3rd isomer. So that gives us all 3 isomers. 1, 2. We have the ketone in the middle, the ketone on one end, and the ketone on one end with a different isomer for the propyl group. Remember, the propyl group has 2 isomers, so we want to be able to do both. All right, so now we have our last one we have, and it is N right here, N. 2 amides with the formula C2H5NO. Okay, so first of all, what's an amide? An amide is a carbonyl bonded to a nitrogen. And so let's start with the simple one, which would be this. So not 3 hydrogens on the nitrogen. There's only 2 hydrogens on that nitrogen. 2, and then H3. So let's see how many carbons we have. Carbons are 2, 1, 2. Hydrogens are 5, 1, 2, 3, 4, 5, N and O. So now we know we have the right structure. We have this right here as a CH3, CH3, and we have all the other things. So, gosh, let's see, what can we do? Oh, we can move this, since this is the aldehyde right here, I'm sorry, since this is the amide structure, we can put a hydrogen here and put the methyl group on this side, and that'll give us our other structure for our amide. Remember, this right here tells us that it's an amide. So this can be a hydrogen or a R group. Most of the time it's going to be an alkyl group, but sometimes it can be a hydrogen. So this would be our other isomer for that. All right, now let's go to 43. We want to do all of these. So we're going to start with doing our three-dimensional formula of our wedges and lines, and then if it has a dipole moment, indicate the direction, okay? So let's do the first one here. I like if you have one different atom, if you make it the one that sticks up, it's sometimes easier to do. I usually draw the other atom that's in the plane. So the two straight lines, the wedge regular lines are the ones in the plane of the board or the paper. And they're just regular lines. And then we have to do a bold wedge out to give the one sticking out toward us, and then a dashed wedge back to the one going back. Now, the carbon-hydrogen bonds are not polar, so we're going to say our dipole moment is going to be all about that fluorine, and it's going to go in that direction. Okay, let's do B. So B is very similar. All we're going to do is going to change one of the hydrogens to a fluorine, and we're going to do this one dashed back again, and this one coming out, H. And now we have a different thing because we have a dipole moment going in this direction, a polar bond going in that direction, which makes our dipole go in this direction here. Okay, see how this is adding to that one, and it's giving us our dipole moment going in a different direction. So our polar bond, our molecule as a whole, has a dipole. All right, so let's do the third one. We're going to do a fluorine here. We're going to do a fluorine here. We're going to do the hydrogen back, and then we've switched out that hydrogen for another fluorine. So we have a CF3. So we have a dipole going in this direction, a polar bond going in that direction, polar bond going in that direction, and a polar bond going in that direction, which makes the net dipole coming kind of sort of out at us right here. So the dipole is coming out toward us. Let's see, we can do the last one of this set on this slide. We're going to have a fluorine. We're going to have a fluorine. Now we have to have a fluorine back here because we've gone to C4, CF4, and right here. And since all of these bonds are polar but pulling in equal and opposite directions, we have zero dipole. All right, so let's see, I can finish two more on here. C2FCl. Okay, so let's go ahead and put the F up here again. Let's put the Cl over here. Let's put a hydrogen back, and let's put a hydrogen over here. Again, I just assign, the two different atoms in the same plane just because it's easier to make sure I draw them correctly and I get them on the molecule without forgetting them. And then I know everything else is hydrogen. So we have a dipole in this direction, a dipole in that direction. This dipole, we have a polar bond in this direction, a polar bond in that direction. This one's a little bit more. So we're going to have a dipole still coming out somewhere in between the fluorine and the chlorine. Okay. Now let's see, FbCl3. So we have a boron, and we have Cl, Cl, and Cl. We don't need to draw any wedges on this. Why? Okay, we don't need to draw any wedges on this because the boron is trigonal planar. It only has 3 electronic zones, and therefore it's going to go in that trigonal planar structure. Okay, so let's do the last few on the next slide. Okay. Oh, that's great. So we have these last 4 here. So let's see, beryllium is one of those ones that also breaks the rule about that. So we actually have 2 bonds, F and F, and that's going to give us a linear structure. So it actually doesn't have a 3-dimensional structure. And we have our polar bonds going in equal and opposite directions, so we have 0 dipole. Oh, I didn't mention, this also has 0 dipole because all the polar bonds are going in equal and opposite directions, giving us that 0 dipole. Okay, let's see, H. Let's see, O and methyl group and methyl group. So our polar bonds are in these directions here. Oh, we didn't draw it in 3 dimensions, did we? We don't have to because the lone pairs are really the ones that are in out of the plane. And therefore we have a net dipole in that direction. Okay, let's do methanol. So we're going to have OH and a CH3. This is tetrahedral but has no dipole. This has lone pairs in and out of the plane. This is a polar bond. This is a polar bond, meaning our dipole is going to go in that direction. Ooh, and now our last one, C2HO. So C double bond O, H, and H. We have a polar bond in this direction, and that is also the direction of our dipole. Okay, so look for the shape of the molecule, and then whether or not those polar bonds cancel out. If they don't cancel out, your molecule will have a net dipole moment. Oh, wow, that's interesting. All right. So let's move on to 46. In 46, which compound of each of the following pairs would have the higher boiling point and why? Okay, so let's look at the first one here. And we have an ether and we have an alcohol. The ether here only has dipole-dipole interactions. The alcohol has hydrogen bonding. Hydrogen bonding is stronger, therefore this is going to be the higher boiling. Okay, so here we have an alcohol and we have 2 alcohols. So 1 alcohol will hydrogen bond and 2 alcohols will also hydrogen bond, but more. So that means 2 types of bonding gives us the higher boiling point. Okay, let's look at this one. This one's a ketone. Oops, I don't want to circle it. This is a ketone right here. And so it has dipole-dipole interaction. And this is an alcohol. So it has hydrogen bonding. So it's going to give you the higher boiling point. This is an ether. And again, it only has dipole-dipole interactions. This one has hydrogen bonding. So it's going to boil higher. This nitrogen has a hydrogen ion. This nitrogen does not have a hydrogen ion. That means that the one with the hydrogen on it has hydrogen bonding available, and therefore it will be the higher boiling point. Ooh, this one's a little hard. We don't have hydrogen bonding, but we do have, let's see. These dipoles are going to cancel each other out, making this have a 0 net dipole. These are going to go in these directions, giving us a net dipole in this direction. So one has a dipole, one does not have a dipole, and they're both the same molecular weight. So the one that has the dipole has a stronger interaction and therefore should have the higher boiling point. All right, let's move on to here. So this is kind of like an alcohol, but it's got that carbonyl, so it's the carboxylic acid. This is an ester, so it's where we've taken that H off and added an R. So the thing is, the carboxylic acid has that hydrogen that can hydrogen bond, making it higher boiling. Okay, this one can't hydrogen bond, it can only dipole-dipole, therefore it's going to be lower boiling. All right, now we're comparing hexane and nonane. So nonane has 9 carbons in it, hexane has 6 carbons in it. They both have the same induced dipole. So whenever you have the same thing, the same interaction going, you have to think about molecular weight. And so in that case, the nonane should have a higher boiling point because it's the same interaction, just more molecular weight. Okay, now our last one. We have this right here and this right here. Let's see, we have a carbon-carbon bonds are not polar. So this should have a very low dipole in this one. This one has a strong polar bond and it should have a dipole. So that means this one with the dipole is going to have dipole-dipole interactions. This is induced dipole, which is a weaker interaction. Therefore, the dipole, one that's a permanent dipole, should have the higher boiling point. Okay, so equate the type of force that it can do to whether or not it's going to have a higher or lower boiling point. All right, moving on to the next question. Predict the IR absorptions for these present in each of the compounds from the previous question. So I've redone them. So what's great is that you can compare, you can tell the difference between the two different compounds by boiling point, or you can look at the IR. So let's look at the IR for this one right here. So obviously all the carbon hydrogens on most of these things are going to be right around 2900 wave numbers, because they're sp3 hybridized. And so they're going to be right around 29. So assume that there's all the carbon hydrogens that are going to be there. And let's just look at the functional group. Okay. So in this case here, the functional group here is the alcohol. The functional group here is the alcohol, and the functional group here is the carbon-oxygen bond. So the carbon-oxygen bond is going to be below 1500. So it's going to be less than 1500. But this OH group right here, that's going to be one of those above 3000. So it's going to be around 3300. And it's going to be big and broad. Okay. So because there's no other functional group here, that's what we're going to see. So both of these OHs on this one right here are going to give you AC, and it just says ACD. All right. So that's going to give us the same as the previous one. So C, how to tell the difference here? In this one right here, we have a carbonyl, and it's a ketone. So that's going to be right around 1700 to 1720 wave numbers. And this OH is going to be 3300. So right away, this one is not going to have any peaks in 3300. This one is going to have a big broad peak in 3300. We should be able to tell the difference in their IR. The next one is D. And in D, we have basically the same thing we had in A. We have one that's going to have a peak at 3300. And then this one's not going to have a peak. It's going to have a peak below 1500 for that other one. So start to assign those functional groups to those different bands we have. We're going to do E right now. All right. This one's going to have a peak at 3200 or above 3000. It's going to have a single slightly broad peak because there's one hydrogen on that nitrogen. Notice that in this one, we don't have any. So we're not going to have that peak at 3200 anymore. All of the peaks are going to be below, all the other peaks are going to be below 1500. Okay, do we see how just changing that one hydrogen on the nitrogen makes it have a peak in the 3200 range and not have a peak in the other functionality? Then we're looking at G here. Ooh, this is going to be a different one. So we have the carbonyl. So both of these have a carbonyl. So we should see something around that 1700 peak, but we know that they shift a bit. So when we have the carboxylic acid, it's going to shift, but it's still going to be in that 1750 range. And we also are going to have a big broad peak. Now the carboxylic acid, because there's more hydrogen bonding, it actually, it's going to be a big broad peak centered around 3000 wave numbers. Okay. Now notice this is not going to have that peak at 3000. We only are going to have that carbonyl peak in the 1700 range. And the last one here. Here we're going to have a peak at 1600 for the double bond. And in this one, we're going to have the peak at 1700 for the carbonyl. So we should be able to tell all the different parts of our just by looking at those different zones. All right, moving on to the next question. Oh, which I already did. All right, write the structural formulas for 4 compounds of the formula C3H6O. Classify each according to the functional group and predict the IR absorption. Okay, C3H6O. So I'm going to draw the linear version first. And 1, 2, 3, 4, 5, 6, 7, 8. Oh, that's too many hydrogens. I got to take away hydrogen. Got to take away 2 hydrogens. So I have to put a double bond in here somewhere. There has to be at least one double bond in each of these isomers because of those H's. So I'm going to put the double bond right here. Okay, so that's our first isomer. Okay, so that's 4 compounds with the formula. Okay, so obviously we have our peak at 1600 for our carbon-carbon double bond, and then we'll have a 3300 big broad peak for the OH. Now we can make an isomer of this. Let's go with a oxygen carbon double bond. So the first one we can do is hydrogen there, 1 carbon, 2 carbons, 3 carbons. Let's see, 1, 2, 3, 4, 5, 6. So we have the right number of hydrogens. So that's great. So this is another possible isomer. And this is an aldehyde. So we're going to see our peak right at 1700 to 1750. So that would be the carbonyl peak, and everything else is just the carbon hydrogen bonds. Okay, well, let's move that and turn it into this isomer here. So all we've done is move this carbonyl over one spot, and that changes it from the aldehyde to a ketone. And so that ketone, again, has this carbonyl functionality, which should be 1700 to 1725. Okay, let's see what else can we draw. Ooh, the last isomer we can draw is that one. 3 carbons and 6 hydrogen, and we've changed the functional group. So we're not gonna have any peaks above 1500. We're gonna have a carbon-carbon peak below 1500. We're gonna have a carbon-oxygen peak below 1500. And of course, we'll have all of the hydrogen peaks. Oh, that's another thing to say right here. In this case here, we're gonna have the sp3 hydrogens below 3000, and we'll have the sp2 hydrogens just above 3000. So we do actually have a difference in our carbon hydrogen peaks on this particular isomer. Okay, moving on. There are 4 amides with this formula, right? Their structures and melting points and boiling points are different. Figure out why. Okay, so let's figure out the amide thing first. Okay, what's an amide again? An amide is going to be this structure here with a nitrogen. Okay, so that takes care of the nitrogen, the oxygen, and one of the carbons. Okay, so let's do 2 more carbons. 2 more carbons right here. Now let's see if we have the right number of hydrogens. We want a total of 7 hydrogens. 1, 2, 3, 4, 5. Oh, then we have to have hydrogens on both of here. Okay, so now we have our first structure. It's our simplest structure. We started building from the amide functionality and then filled out our carbons and hydrogens from there. Okay, so the next thing we do is there's 4 of them. So we got to change the isomer. So let's see, we can't do anything with this chain. There are no isomers of this ethyl substituent right here. That means we have to move something else. So let's see. So if we take one of these methyl groups and move it to the other side, to bond it to the nitrogen, that'll be one of the other isomers. So let's do that. And so that structure would look something like, let's see, we're going to draw our amide first. Right here, we're going to put a methyl group here, and that other methyl group's going to move over here, and we still have to have that hydrogen. Okay, so that's our second isomer. Okay, how are we going to do the next one? Well, let's move this methyl group to the other side, also to the nitrogen, the other methyl group to the nitrogen. So we're going to draw our amide here, and if one methyl group's here and one methyl group's here, that's going to put the hydrogen here. So that has to be the one isomer there. So there's 4 amides. What is the other one possible? Let's see, we've moved that one there, we've moved that one there. Oh, we could do it this way. We can take this right here, and instead of moving just a methyl group, we're going to move an ethyl group to the other side. And this one's going to have a hydrogen here. All right. Now it says one of these amides has a melting and boiling point that's substantially lower than the other 3. So looking at this, I see this amide can hydrogen bond. This amide can hydrogen bond. This amide can hydrogen bond, but this one cannot. So I think that one has the lower boiling point because of that. So that the fact that it cannot hydrogen bond. Okay, so now the next thing it says is how would these how would the IRs change on this? Well, this should have 2 peaks above around 3,200 because it has 2 hydrogens. So it should have these 2 peaks in that range. This should have 1 peak in 3,200. This should have the 1 peak in 3,200 because of the hydrogen. And this should have 0 peaks at 3,200. So this is going to be missing the peak at 3,200. And therefore, we can distinguish the difference between this one and these 2, the 2 in the middle, and the third one, just by looking at the IR spectrum. Okay. All right. So let's see. That's number 51. And that is our last question for this homework on chapter 2. I hope you found that explanation good, and I will see you in class.